Good morning, everyone. Welcome to this Spring Knowledge Transfer event, and thank you all for joining us today, alongside the team behind Pipebot Patrol, an Ofwat-funded innovation project led by Northumbrian Water, which aims to prevent pollution events by detecting and removing blockages as they form via an automated sewer-safe robot. To get us started, I just want to play a short video introducing Spring Innovation for those who don't already know us and our role in supporting innovation and collaboration across the water sector.
In our industry, innovation is happening everywhere, every day. With so much going on, it's hard to keep track. The sector is tackling big, urgent challenges, like climate change, aging infrastructure, and more, but not always in a joined-up way. That's where we come in. Spring is the central innovation hub for the water sector. We gather insights from hundreds of projects across the UK and Ireland, showing who's doing what, what's working, and where the next big transformation could come from. We connect problem owners with solution providers globally, both inside and outside the water industry, to share knowledge, find partners, and accelerate ideas. This means less duplication and more efficient use of time and resources. Whether you're looking to learn from others' experiences, find collaborators, or share your own solutions, Spring makes it easy. Together, we're speeding up innovation, driving transformation, and shaping the future of our industry, both in the UK and Ireland. Spring, accelerating water sector transformation.
Great, so I hope that was a helpful guide for anyone who was unfamiliar with Spring before today. So just to summarise, Spring is here to help you deliver against Ofwat's expectations for best practice knowledge sharing across the water sector. And we're supporting delivery of the Water Innovation Strategy 2050 objectives through our knowledge sharing service, which supports the transfer of learnings from an innovation project to the wider sector, creating project legacy that helps innovators ultimately to identify and adopt the right solutions at a greater pace. So we actually partnered with Ofwat, the economic regulator for England and Wales in the water industry, to build a view of what best practice knowledge sharing looks like. And the 6 principles we created were to learn from what already exists before committing to innovation projects. And to aid this, we created the Spring platform, which hosts a multitude of project case studies aligned to the priorities laid out in the Water Innovation Strategy 2050. And we're also working on other tools to ensure innovation intelligence is easily accessible to the sector. The second one is to target innovation insights to the right audience to meet our objectives. So, for example, do we have the relevant people on this call today and who can take action on the knowledge within their own organisations? Number 3 is that insights are regularly shared through multiple channels from day one of the project. Historically, we know knowledge share has happened at the end of a project, and we really want to start moving towards a model where we share from day one. That sector knowledge is open and centralised. That one's quite self-explanatory. Obviously, it's a lot harder to learn from knowledge that's in all different places. So we really want to be centralising that knowledge all in one place. Insights from both innovation successes and failures are shared. So as we all know, the failures are just as important to share about as the lessons of success. And hopefully we'll hear about some of those from our presenters today, the challenges they faced and how they overcame them. And that people are empowered to receive and embed lessons from external sources. So back today, I'll share a little bit about the agenda for the session and introduce our speakers before I hand over to them. But before I do, I just want to remind the audience that, as always, we will be launching our poll during this event to gain your thoughts. And answering our poll is the most impactful way that you can help us make sure that these events are providing value to you, your organisation, and the wider sector too. And that these showcases are supporting our goal of faster paced adoption of solutions. Your insights not only help us understand the actions that you plan to take on the knowledge shared today, but if there's anything more we could have done or shared to ensure the successful transfer of the key insights from these innovation projects. We'll launch that poll at the break, so please do make sure to submit your answers when you see that, and we'll launch it again at the end too. So to begin today's session, we'll hear a little bit about the importance of knowledge sharing and the context setting behind Pipebot Control, and then we'll go into a brief technical summary. followed by a project roadmap and implementation guide. And we'll hear about the projected benefits from all of this great work. We'll go for a quick break and then we'll come back to do a deeper dive into the lessons learned and challenges that were overcome, and then finish up with our Q&A. So do make sure to be putting your queries in the chat throughout today's session for our presenters, and we'll make sure to get those answered in the Q&A for you. Just to quickly introduce our speakers before I hand over, we'll start hearing from Clive Sermon-Wells, Innovation Partnerships Manager at Northumbrian Water, Jessica Richardson, Project Lead and Metronomics Engineer, Shane Egan, Technical Director, Kirill Horoshenkov from Professor of Acoustics, and Chris Bolt, Innovation Portfolio Manager. So without further ado, Clive, I'll hand over to you to kick off.
Hello, thanks very much. And thanks everybody for attending the session. Before we jump into my introduction to Pipebot Patrol and the rationale for the project and the problem that it's aiming to address, I thought I'd say just a couple of words to reinforce what Leah has already said about knowledge transfer. We see the spring showcases as an absolute crucial means of conveying our projects and in gaining knowledge about what other people are doing and what they're learning, so that we can incorporate that into our future projects as well. We've had some great leads. One great example is United Utilities 3D printing, concrete printing project, which we heard about through the spring showcase and followed up, and now we are pursuing that and implementing it at Northumbrian Water. So these events really do lead to other people taking things on. This is one of many approaches that we've got to disseminating and hopefully leading on to implementation and adoption of projects through Pipebot Patrol in particular, but all of our Ofwat Water Breakthrough winning projects. We generally will use a website. So Pipebot Patrol has its own website, which gives status and background information, video updates, and so on. Our Innovation Festival, we have showcased this project twice there, and we intend to keep doing that. General industry conferences as well, and user groups. I've been around speaking about Pipebot Patrol to a number of other groups who are involved in flooding, general engineering as well. So let's move on to what you've come, the main meal of the day, if you like, the Pipebot Patrol project. And we'll start, I want to just set the scene really, because I'll not assume everybody in the room knows what sewer flooding is, but there are some fairly graphic images here of what that means to our end customers. This is the worst thing that we can do to a customer. External flooding, which you see on the picture on the left, and internal flooding, where the toilet is overflowing with other people's sewage. And these are really generally caused, not exclusively, but most often caused by blockages in the sewerage system, in various parts of the sewerage system. And there are all sorts of causes of those blockages. There are 300,000 or so blockages on the sewerage network that are dealt with by UK water companies every year, and that costs the industry £100 million a year. And the Cunliffe report said that 40% of these spills are related to customers' own behaviours. So things that are being put down the toilet, like wet wipes, or down the kitchen sink, fats, oils and greases, all leading to problems later on that affect so many people. And you can see from the pie chart that there are many causes that we are attempting to address through this project. So the overall goal of the Pipebot Patrol project is to prevent these blockages from ever occurring. Let's just move on to the next slide. I've got control here. Let me just take control, and then I will move on to the next slide myself. There we go. So it's not like we don't do anything to address this problem. We've been working on it for years, and there are a number of fairly effective approaches have been adopted over the years. So, for example, behaviour change campaigns is one way of addressing blockages. Our Northumbrian Water's own Bin the Wipe campaign is a campaign that encourages people not to put wipes down the toilet. But of course, Not everybody complies with a behaviour campaign, and they need constant endorsement, and eventually their effectiveness wears off if they're not reinforced. Another approach to dealing with blockages, if we have an area where there's a blockage hotspot and we have frequent problems, we will create a planned preventative maintenance and send out routinely a team to look in the manhole on spec to see whether the blockage is building up there or not. And of course, that's quite wasteful of resources, because often we'll go out to a site and find that there is no blockage, and therefore that journey was a wasted journey. And blockages can occur in between these speculative inspections. The final approach that we have is using predictive models. So we have, most water companies will have sewer level monitors, quite large networks in some cases of sewer level monitoring devices. That's a gadget in many manholes that is measuring the water level. And if you see water levels rising at one point, but not rising downstream, then the chances are that there is a blockage between those 2 points. So that's giving new insight. It's allowing teams to react and get out and try and deal with those blockages. But there are a few flaws in that approach. I'm a big fan of predictive models, but we can't always react in time. And if we have very heavy rainfall, then our alarm dashboard will go mad and we'll not be able to address every single event before flooding occurs. Also, these models don't tell you the precise location of the blockage, nor do they tell you the characteristic of the blockage, whether it's being caused by fats, oils and greases, wet wipes, tree roots, debris, soft blockages, that's paper and poo. So we don't get any intelligence from that. So those are the approaches that we've taken in the past. Now, we came up with this vision really by talking to the people involved within Northumbrian Water and across the water industry in dealing with blockages and preventing sewer from happening, flooding from happening. And the message we were receiving was, if only we could determine the precise location of debris buildup before it actually caused a total blockage that was going to lead to flooding, then we'd have enough time to get out to site to solve the problem and clear it before the heavy rainfall came, for instance. So if we could monitor it in some way and monitor everywhere all of the time, that would be great. So that seemed like a challenge to us, and we threw our mind to the world of films like Thunderbirds and Disney Pixar's Wall-E, and came up with the concept of, what if we had a sewer crawling robot that literally lived in the sewer and monitored the whole time, 24/7, a particular sewer zone, and alerted us to the buildup of debris. That would mean we would learn a huge amount about how a particular sewer zone functioned, how blockages occurred and what they were made of, and how they moved through the system, and how they eventually became full blockages, and over what period of time. It will give us a completely new vision and a new visibility of how that occurred. So that was our concept, and we thought, well, we could invent a robot that did this. It would have to work autonomously and live in the sewer, as opposed to being put in and controlled by humans. So that is the concept that we came up with, and we converted it into a bid in the Ofwat Innovation Fund, the Water Breakthrough Challenge, 2 rounds ago. And we put forward a proposal to develop this autonomous sewer crawling robot, which is the first component, number 1, that would live in the sewers but would have a dock in a manhole or inspection chamber. That's component number 2. But that we could see what it was doing all of the time through a dashboard that would tell us where the build-up was precisely. That's the sort of human interface, the third part of the system. There was a fourth part of the system in the bottom left that's greyed out, and this is tools for clearing blockages. So we decided to draw a line in our project over blockage clearing and make this first phase of the project about establishing proving the concept that a robot can live in the sewers and can survive the harsh conditions, can alert us to the build-up early enough for us to react to it, and that we would add blockage clearing tools in a future phase so that we could actually tackle maintenance of the sewer as well as just alerting a human team to come and deal with the blockage at this stage. There's a couple of things to point out on here as well. That's that big black line that goes between the inspection chamber with a reel in it and a line which is a tether that goes to the robot. So in the first instance of the project, although the future vision was that it should be completely free to roam and perhaps battery powered, in the first instance it should be tethered for a number of very good reasons. But I was advised not to go straight to an untethered robot because it would be too ambitious at this stage. The second thing you can see is above the cable reel in the manhole component 2, there's a kiosk on the ground. So if you're going to supply mains power, unlimited power, and unlimited data via a cable, you need a means of transmitting that back. So in the very first concept, the bid we put forward to Ofwat, we said that we would establish 3 zones for testing in the field once we developed the robot, and they would transmit data from a kiosk that will be established. So others in the group will say more about that as we progress on. I'm just going to throw this slide up and give you a second to read it while I talk briefly about it. But as soon as you start to put forward quite ambitious and very, very difficult to do ideas, you get a whole load of reasons why you wouldn't want to do this project and why it won't work. I'm pleased to say that we've managed to prove pretty well all of these wrong, or we've managed to overcome them by one guise or another, engineering them, most of them out. So again, we'll talk a little bit more about that later, but it isn't without its incredibly difficult challenges. The good news is Ofwat Water Breakthrough Challenge did award funding of £1.6 million to the project, taking the total budget to 1.8 million because the partners obviously contribute. It's a 2-year project which started in July 2024, and the main partners in the project are Sheffield University, who are providing robot autonomy and acoustics expertise, Minicam, on whose CCTV crawler the initial concept product has been based, the CRP 140, EMS, who are used in the project to get power and data to difficult to reach places. Northumbrian use EMS for supplying data, getting data and power to riverbanks for water quality monitoring in rivers, for instance, those kind of difficult to get to. And 2 water companies who partnered in the first phase from a subject matter expertise point of view, Thames Water and Southern Water. We also engaged 3 local authorities, Newcastle, Gateshead and Sunderland, because we realised very early on that although the project was primarily aimed at water company use for prevention of sewer flooding, that the idea could be applied to highways drains as well, surface water only. And that's why later in our project, when we've chosen test zones in the field, we've chosen 1 foul only sewer, 1 combined sewer, and 1 surface water only sewer. So the last thing I'm really going to say at this stage before handing over is just to make clear the objectives. We weren't aiming to produce a production ready final system at this stage. That's the next bid that we're putting forward. At this stage, we were looking to prove that we could develop true autonomy in the sewer from a robot, that it could survive for 30 days unattended by a human. That means literally putting the lid on the manhole and walking away and letting the robot patrol the sewer for us. And that it should be able to alert us to the build-up as they form rather than afterwards. So at that stage, I'll hand over to, I believe it's going to be Chris, to talk about the next stage.
Perfect. Thanks very much, Clive. So my job today is to take you through the project timeline and hopefully give you a little overview of how we've progressed and moved along. So for the project, we have 4 phases. So the pre-phase, as Clive kind of alluded to there, we've done work at the Innovation Festival with that, which has been a great environment for us to showcase what Pipebot Patrol is all about, to be able to gain a really engaged stakeholder group and also gain some knowledge to really inform what we do going forward. So we were able to do that prior to the project beginning in July 2024, and also some other kind of preparatory activity where we were able to set up project management processes and practices, establish our working group and meeting frequency, and then also everything that we need for collaboration with partners. And that led us nicely into phase 1, where we were able to sign the collaboration agreement, obviously crucially at the start, and engage in workshops with stakeholders, and also include people internally at Northumbrian Water to get their perspective and opinion on it, to really feed into the development of the robot and the dock as well. And obviously it's really important that we consider all those different aspects and make sure that when we're looking to develop, it's really been well thought out and also well socialized amongst those people as well. And then we've also got on there that we explored different communication methods before settling on the route that we did with the kiosk as well. So so quite a key phase that we were until July 2025, but then that had some overlap with the development and testing phase that began. And I don't want to touch loads on this because I know we've got stuff coming up on that, but we were able to engage in lab-based test scenarios using the Integrated Civil and Infrastructure Research Centre at University of Sheffield to really make sure that we were testing the robot thoroughly in an environment that was appropriate and that was going to best lead us into our progress going forward. So all of that testing has been done in nice, lovely environments for the robot. But then we've also been developing a dashboard as well as a control panel. So those are kind of 2 separate aspects, with the dashboard forming something that can be looked at and can show data and display that, whereas the control panel is something that would be used to interact with the Pipebot. And then phase 3, which we have moved to quite recently, November 25. So this phase is taking us from that lab test environment, which, like I said, is quite nice and controlled, to moving us into testing in live sewers. So this is a really exciting time to be part of the project, where we're going to be putting the Pipebot into a sewer later on this month, as you can see from the milestone down the bottom of this slide. So just prior to putting the Pipebot into the live sewer, there's been lots of work for us to do, and lots of kind of preparation for that, obviously with kind of practicalities and logistics of that. But then the plan is for us to conduct all of our testing in that environment, and then be able to further review this and engage with all the kind of people on the project, and be able to review our outcomes following that on-site testing, and complete any further work and adjustments following that. And then also included on this slide, we've just popped on about the release of documentation and further dissemination. Hopefully we might be invited back to do another showcase, and really just to build on what we learn in the next sort of 9-10 months that we can share. So I was moving on to it there. So the next steps for the project we've kind of grouped into a few themes here. So I mentioned really important to us is our on-site testing. So being able to test all the different elements that we have, so the dock, the robot, the control, and the visual dashboard as well. So making sure they all work in the practical environment are crucial to what we want to achieve. And then expansion to further test sites. So we have one test site initially, but being able to expand that to further sites once we're happy with how testing is going. Then we also have development. So obviously the point of testing is to improve anything that's required and to make sure that we work to develop that and iterate that further. And also as part of that development stage, we're hoping to continue with socialization of the Pipebot with some of our field teams engaging with it, and being able to just, again, it's just really embedding the idea of using a Pipebot within the business, which is really important as part of the project, to be able to make sure that people realize that a Pipebot is going to be something that is used in the business and can really help the work that we do as well. And then finally, another key step is engagement, and that is both within our industry, within the water industry, and also wider. So whether that's engaging, as Clive kind of said at the start, with lots of different forums, groups, and different bodies, but being able to engage the public in this as well, because they're people who are really involved in this and will be affected or hopefully beneficiaries from this. So making sure that we're sharing this really interesting story with them. And we've already done lots of engagement at sites where we're testing. And then, like I said, some more lessons learned as well. And then I guess finally from me, I just wanted to reiterate our expectations of the project. We have some really ambitious goals. Clive set them out, but we're expecting to meet those goals and being able to collect data to communicate from the robot to the dashboard, be able to locate blockages and have autonomy within the sewer, all key aspects. And then I think really important to us is that it can stay in the sewer for that long period of 30 days and be able to be durable in that time period. So we expect to meet all those goals and then to further refine those and create some learnings, share them, but then hopefully we'll be building on this project as part of Pipebot Patrol 2, which we're hoping will be successfully funded. And we can then build on these project outcomes and look at some of the even more ambitious goals going forward and how we might achieve those and take the work that we've done here and just kind of translate that forward. So they're my slides. I'll pass over to Jess and Shane at Minicam.
It's probably worth me saying, just adding about the 30 days while Shane and Jess are getting themselves ready, is that this is the 30-day duty cycle. We're not talking about then taking the robot out. What we're talking about is it should be able to work for 30 days before it needs any maintenance. Quick maintenance cycle and then back in for another cycle, or we decide to put it into a different zone altogether if we now understand what's going on in that. So I'll hand over.
Hi everyone, so it's Shane and Jess here from Minicam. So we were brought on board as the industrial partners really, so we're the ones that can, that's job to make the cartoons and the graphics into reality. So our background's in producing what you probably all know as kind of typical inspection systems, from crawlers to push cameras. So we have the experience to bring this to a reality. So we're going to cover the technical overview, kind of high level, not getting into too much detail, but give you a flavour of what we've set about. So at a high level here, we've got our kiosk, which is the above ground control unit. We don't expect that to be here in the future stages, but that's a necessary evil for us. We've got a cable reel. The cable reel is above ground as well, located in the kiosk. And that's responsible for tethering the robot, passing all the data and communications back and forth. In this project, we're supporting cable reels up to 350 metres. We have 500 metre cable reels, but we hope in future to avoid that completely. It's been quite a technical challenge around installations on site. And then we move over to in the manhole. So we have a dock in the manhole, and we'll cover that later on. But the whole purpose of this is we need a way of getting that robot out of the flow. So we, in high water, high flood event situations, we were not the ones causing additional problems. So the majority of its life is spent in the dock, and it goes and travels down the pipe, roaming, looking for problems at intervals. And then we've got the robot as well. So the robot's equipped with a lot of sensors. It's based on one of our existing robots. So the thoughts and ideas here are, how can we deliver and improve this technology as quickly as possible without completely reinventing everything and making everyone wait many, many years to develop a ground-up solution. So we have based all this off our existing equipment. It's kind of adaptations and add-ons to our existing equipment, all to prove the technology. And once we've collected all the data and we've got everything, we're working with Northumbrian to integrate everything into dashboards so that key stakeholders can monitor and understand what the situation is in the pipe, and make the correct actions, whether it be that going jetting or sending a crew out to do some work on the pipe. I'll pass over to Jess to talk about our crawlers.
Yeah, so our first task was to integrate all the various sensors into our existing crawler, as Shane said, so that the technologies can be used in harsh environments like sewers. So we first laid out the criteria that we needed to meet, which included positioning microphones in relation to the speaker. We needed a camera and enough lighting to be able to take photos while we're down in the pipe to back up what the sensors were finding. We needed to house the supporting electronics on board the crawler, which also included having a LiDAR and IMU sensor. We were optimising the arrangements for 300mm diameter pipes to begin with, and we also needed to make sure those sensors were protected, as well as allowing for data transfer from those sensors up to our control unit that lives in the kiosk. Once we'd agreed the specification, we could then move on to our CAD design. So you can see on the left, we've got the radial array, which holds 8 microphones around a centralised speaker, and we're going to be using those to detect blockages and defects in the pipeline. The next array has got 4 microphones that run down either side of the crawler body, and we're hoping that this will be successful in detecting blockages in the lateral pipe connections. We've got a LiDAR sensor that's placed on top of the crawler, which we use for near field detection and enhancing the autonomous control that we have. We've got a small camera that we already use in one of our other products, and additional LEDs that we have at the front of the crawler, again to back up what those sensors have detected to display on the dashboard. We've got the supporting electronics are all housed in the arm of the crawler, which includes an IMU sensor that we use to determine the position of the crawler within the network. Once we'd all agreed on the CAD design, we could move on to our PCB design. So we designed new schematics to make the power supply that we have on the crawler already compatible with all of the additional electronics that we were adding in, as well as designing PCBs for the microphone arrangements and then the camera LED interface as well. Then we could get on to the prototyping stage. So incorporating the 2 mechanical and hardware designs, it made us able to determine whether our setup will function practically, and then we can make any adjustments and do any tweaks as and when we need before we commit to purchasing any machine parts. So all of that has brought us to our machine prototype that we can see here, and this is what we'll be using in our first field trials within the sewer network over the next couple of weeks. It's anodized for extra protection in the sewer network, and it's also pressurized to prevent any water ingress. And then we've also added a more powerful gas strut to stabilize the crawler a bit more to manage the additional weight of the electronics and sensors that we've added in. And then Shane's going to talk you through the dock development cycle as well.
So the dock, we started off with a couple of concepts. I think initially actually started with concept 2, which is quite a complex arrangement of a cradle, trying to bring the whole thing up as in one, sits in the bottom of the pipe, but generally in the world of sewage and wastewater, complex doesn't usually go terribly well. So we pushed for how can we simplify this and make it so simple that it can't go wrong. And we settled on concept 1, which was a simple rail system where, because we're tethered, you naturally can drag the crawler backwards and it can slide up its rails. No mechanical moving parts, nothing to go wrong, reducing the risk of us being the problem in the pipe rather than solving the problem. So we settled on the design. We then started, as usual, our CAD design, come up with some concepts, design in 3D prototypes, and we first started out with quite a solid design, but realised, well, we all know no two manholes are the same, but they've got much more variability than we expected when we actually went on site and assessed them. So we started with a modular design with different telescopic rails so that we can fit into a variety of manholes, and we can fit into a variety of depths of manholes, so we're not actually limited in where we can go. I think the other interesting thing was during some of our testing, we actually realised we needed to reduce the friction on the handles. So we again find the simple solution. Don't overcomplicate things. So went for beads on the handles to reduce the friction, so it can slide nicely up its rail system. So here you can see some of our prototypes from making something wooden in our lab, and there you see we had handles that were quite high friction. Didn't work particularly well through a lot of testing, so we performed IKEA style testing where it just goes back and forth. Did hundreds and hundreds of docking scenarios to try and make sure this thing is reliable. And then you can see further on the right there, we are installing it in a lab manhole. So that's at the University of Sheffield's lab, where they've got a really nice facility where we can do simulated real testing, but actually in the environment of a lab. And then here's a short video just showing the action that the robot takes. So hopefully that plays. It does. So very simple, drags itself up, does end detection at the top, and then the crawler will sit there, and the way the cable wheel's designed means that will stay there for as long as we need. And in the event we want to do a survey, it drops down the rails, it's in the bottom of the manhole, and then it will continue through. We've also incorporated guide rollers there to do cable management so that we're not causing problems with the robot tangling itself and causing more problems in a sewer that we're trying to solve problems in. I think we are on to Carol's section now.
Good morning, everyone. Let me just take over the control. Okay, I press the button. So here we are now. Okay, so next slide. Can you see the next slide?
We can.
Good, good. Well, I'm Kirill Haroshenko from the University of Sheffield. Quite a lot already been said about sensor payload. and University of Sheffield been heavily involved in developing sensor payload for not only detecting the artifacts in the pipe, like blockages, but also for the navigation. So to make sure that the robot knows where it is, and the control center knows where the robot is as well. So without actually keeping an eye all the time on it. So traditionally, this crawl has been only equipped with the CCTV, and only visual images were analyzed. Unfortunately, visual images are not very helpful for real-time control if the robot is fully autonomous. And the reason why, because there is a lot of information to process, and as a result, it takes a long time to analyze visual images and make sense of it. So in order to overcome that, we added a new sensor payload, so such as 2D, let me just see if actually, such as 2D LiDAR. We also added the array of microphones. The previous speaker showed actually can be deployed either on the front of the robot in here or on the side of the robot in here. It was a question about IMU. IMU is inertial measurement unit, and it basically detects vibration of a robot and can be used for several things. Let me just tell you what it can be used, all these things can be used for. So in addition to the camera, microphones and the speaker can be used for the long-range detection of blockages in pipes, but also other artifacts like lateral connections and manholes. Unlike video cameras, so it can detect blockages tens or even hundreds of meters away from the robot. So therefore, the robot can actually plan its path using acoustical data to say, okay, well, I detect something, say, 20, 30, 40 meters away. So I need to go there and examine it. So once it gets in there, so actually it continues to engage LiDAR, and the LiDAR will continue to provide the robot with the very accurate information, much more accurate than acoustic sensing. Acoustic sensing may give us information about within a few centimeters, whereas LiDAR gives us information within 10, 20 millimeters accuracy. So therefore, when the robot gets to artifacts like lateral connection or blockage, it can examine it in really high resolution details to make a judgment what it is. IMU can be used for several things. One is actually to detect where a robot is. So by integrating the accelerometer data and finding out how far a robot went in terms of the eastings, northings, and elevation. But also we can detect what is the surface over which the robot is driven on. So for example, it can detect joints, so and this distance between the joints to support navigation, but also it can actually detect whether the surface of the pipe under the water covered in silt, debris or gravel, or just naturally rough. I'll show you some of the some example of the data we get with this system. So the bottom picture in here, so it is basically our setup at the University of Sheffield. It's 6 meter long, 300 millimeter pipe connecting two manholes, some of which you can see actually in here. And as I said, the robot sends a acoustic impulse or sine sweep and finds out where things are. And as it drives along, so it can actually get really high resolution map. You can see in here with the LiDAR, detecting all the artifacts as small as the joints and also the geometry of the manholes and the blockages, if any of those blockages actually exist in there. So all the sensors actually, so they provide reasonably low amount of information so that the signals can be processed in real time. So the robot, which may travel with a speed of a few centimeters per second, so can actually make decision by itself. So is there a blockage? If there is a blockage, can I pass it? If I can't pass it, so well, where do I need to stop? And shall I go back and report it, and so on and so forth. I'll show you a video. So basically just an example of a blockage which we put deliberately in the manhole. So the robot will come out, detect this blockage, and make decision to go back. So what you see in here is all autonomous. There is no human being sitting in front of the joystick actually, so all the decisions are made by the robot brain, which is basically Raspberry Pi. So it comes out, it detects blockage well before it can see it. So it comes close enough. You can see the spinning LiDAR in front of it. So the spinning LiDAR estimates the blockage is too big for robot to pass over, and it just retreats back to its original position. I think I'm done now. So it's Sonia now.
Thank you, Carol. Hello, I'm Sonia Ostradin. I'm Head of Innovation in company Environmental Monitoring Solution, now Kyocera Water. So our role within this project was to enable and ensure secure data flow. You can see a schematic on your screen. On the left side is data flow between robot and dashboards and telemetry units, which are hosted by Northumbrian Water. On the right side, there is a schematic of a kiosk. And yes, we are going to try and remove kiosks. We are going to make a good use in the next project. But kiosk is a little bit bigger than we anticipated, simply because it has to host a reel and tether that hopefully we will lose in the future. So requirements were to provide secure data connection, remote connection to the system, receive diagnostics and positional MQTT messages from the robot, receive files from the robot, video and images files, and LiDAR sensor data, and then kiosk, door alarms, and gas sensor. To do this, Kyocera installed a router that uses GSM signal to provide data connection. Router select acts as a gateway device, allowing for a secure VPN connection on the network and inside the kiosk. And router provides data connection to all devices in the kiosk, either via Wi-Fi or Ethernet, including MCU, which is control unit, minicam, and Raspberry Pi, which sits on a robot. There are more details which are quite technical, so I'm not going to present here, but we can have a separate conversation about that if anyone is interested. Very important for any innovation project is steep learning curve. We started with one concept completely changing during this project, but we were working alongside Northumbrian Water telemetry and security team, which is very, very important because this is robot living in a sewer. So I will hand over now to Clive.
Thanks, Sonia. So a couple of things to add to this one. We've decided that there is a need for two different control panels, dashboards. So in the original concept diagram where we had three components, you saw one picture of a sewer health dashboard, which was really designed for operational users in the wastewater team to highlight the points of interest that were being monitored, the severity of the debris buildup and so forth, and give them some kind of prioritized view based on this information coming from the robot in its daily and more frequent than the daily patrols of the same pipes as it was monitoring and watching what was actually happening and how it was growing and moving. The second dashboard that we decided we needed was a robot health dashboard. So as far as a water company operating this is concerned, we really just want a red, amber, green on whether the robot is healthy and operating. What we're really interested in is in the operation of the sewer itself, and whether that is in a good state of health or requiring maintenance. So those are the two dashboards. Couple of other things that I just wanted to point out there were, so what is this information that's coming back and forward precisely? Sonia mentioned some of the different kinds of data set, but there's a couple of really important ones. It's not just data, it's commands. So as an operator of the system, there is a need like above all else, to know where the robot is at any given point. So it has this inertial positioning system that's used in things like tunnel boring machines and other underground applications where GPS won't work, to tell us and leave a breadcrumb trail. So we should know where it was when it last communicated with us. So even if it died or it lost communication, we still have a last known position, an easting and northing of where it is in the worst case scenario. Not that knowing where it is will affect its operation. It's just that we want to know where it is. And of course, there's a whole load of mapping opportunities that open up if you are repeatedly going up and down the same stretch of pipe. There's a couple of commands that we need to issue as well. One would be, come back to your manhole, we're recalling you. Okay, so this is a recall message command that the robot has to obey. If, for instance, we know either that there's extreme flow coming down that pipe due to very, very heavy rainfall or a storm, might want to recall the robot. Second thing is, if we decide we need to do some maintenance, we need to get in there through other means, we don't want the robot getting in the way or getting tangled. So we can force it to be recalled to its manhole. And a message the other way is, if the robot were to run into some kind of problem, either a sensor stops working or it becomes immobile, its battery dies, whatever happens to that robot, it can always send a distress signal down the cable to us to say, I'm at this location, come and rescue me, I'm immobile. So those are really important little pieces of data. So let's just have a high level view. These aren't learnings as such. These are conclusions that we have drawn that are being fed into the next phase of the project. So remember, our goal here, we've realized there are many, many other opportunities, and we've seen one or two of those flashing by in the chat. You know, could it do this? Could it carry that sensor? Yes, it is basically a mobile sensor. Okay, that's what it is at heart, and we are proving it can survive the harsh environment of the sewer, and that it can be truly autonomous, even in its current tethered format. The idea is absolutely to lose the tether in future, because the tether becomes a major constraint. One of the biggest problems, preventers of scaling and adoption of this in wide scale across the water industry is the fact that at the moment, in its current form, you'd have to build a kiosk next to every launch inspection chamber. That is just not feasible. That is never going to work. So the other thing is the tether becomes a massive constraint because of the distance limitation it imposes. Theoretically, it will be we should be able to go way further than the tether would allow us, and branch and go around the sewer in multiple directions and so forth. But the tether constrains that at the moment. But that's no problem, because we only introduced the tether, remember, to give ourselves an unlimited power and data supply so that we can then size the batteries in the next phase and come up with a suitable means of communication for wireless in future, knowing the volume of data that's needed. So number one, realization, we're going to have to lose the tether in the next phase. Number two, as the robot became more complicated, it became fairly quickly apparent that if you wanted this Pipebot to clear blockages in future, that we were facing this kind of Frankenstein effect where we were building more and more things onto the robot, and it was becoming more and more unwieldy. It was a much more sensible approach to actually have a patrol robot in future and a maintenance and blockage clearing robot in future. So one does the patrolling and is tuned and designed specifically for that inspection purpose and for sensor carrying, whilst the other is very much dealing with maintenance of the sewer. And we talk about blockages at the moment, but if you imagine a future where many sewer zones are being patrolled concurrently, simultaneously by many robots coexisting in the sewer, theoretically, nothing ever gets to the point where it is a blockage, because the sewer's being maintained by a robot. It's being cleaned, and it theoretically can be done as the debris is building up. So what we might not see in the future here is robots with sort of radical tooling designed to clear blockages, rather more debris clearing robots that just continually continually cleaning and scraping and moving debris and trying to break it up a little bit so that the flow can take it away. If we can get to that situation, then blockages theoretically would never be allowed to form. There was a question as well in the chat. The robot was originally designed for 10-inch sewers, 300mm sewers, and we chose that size based on quite a lot of statistical analysis of the Northumbrian Water complete sewer network and the sizes of various pipes and the materials and so forth, and making a decision that let's rule out the laterals, the 4 and 6s, for now, in terms of getting into them. Let's concentrate on survival, ruggedization, and later on we can worry about miniaturization. And in the next phase of the project, we are thinking about launching a child robot and the viability of doing that, a tiny robot. That's hence the Thunderbird's idea. Thunderbird 2 used to was basically a tool carrying Thunderbird that could deliver another Thunderbird to the site as needed. So that's what we're thinking. Maybe our parent host robot can launch a child robot upper lateral, but we'll see on that one. That's in phase 2. But we're definitely going to miniaturize the robot in phase 2 to more like 8 inches and increase stability. One of the reasons we went for 10-inch, close to the diameter of the pipe that it was going to be roaming in, is the actual size of the robot created a certain amount of stability, but that again is not scalable. What we need is something much more flexible and adaptable. The final thing, thanks for that picture of Thunderbird 2 there, is the ATEX compliance. So obviously anything we put into the sewer has to be ATEX certified. And what we're doing at this stage is we're using very low risk zones, and this was one of the factors in our choice. But we know that to scale this idea, we need to have an ATEX compliance solution that can be put into any sewer regardless of its type. So that's basically all I've got to say at this. Oh no, I haven't. I've got one more. This is a quick heads up. This is one of the slides that we have just prepared on the next phase of the project. So we're thinking a patrol robot, okay, with its batteries, untethered, and a maintenance robot. This one's got a flail on it and a drill and a scoop. These are artists' impressions. Remember, they're not real. They're not real robot concepts. They're going to be thrashed out during a very detailed and quite lengthy specification and design process with hopefully many of you people. Some ideas about how the battery to battery charging could work. Remember, we can't have mains power in manholes. It's just not scalable. It takes too long anyway. So we've come up with an idea borrowed from the world of e-scooters, where a human changes the carousel of batteries that power the scooter in that case, but in this case, a robot. So we're thinking of a modified chamber lid with a carousel of batteries that are used to charge the small batteries in the robots inductively, and that it will be a lockable, alarmed manhole cover. And again, remember that the robot spends little time in the chamber. It spends its time roaming around the sewer network. It only really comes back down to charge its battery in the future. It can transmit data from where it is, whether or not it has a tether on it. So I think that is all I had to say, and I'm going to hand back to Leah to talk about what's going to happen next.
Great, thank you, Clive, and thank you to all our presenters so far for a really engaging presentation. Thank you to the audience as well. There's been a lot of questions, so it's great to see people are engaged and finding the information interesting and valuable. In that vein, you'll see there is a QR code on the screen. We would love your feedback if you are finding this showcase interesting so far. That it really does help us shape what these showcases look like and how we can deliver more value to the audience of these showcases. So please do fill that in as we go to a break or before you leave if you have to get off. We are going to go to a short break now. We'll be coming back. I'll just do a 5-minute break since we're running a little bit over time. So the time is 11:01. We'll come back at 11:06. Your cameras and mics are already off, so there's no need to leave the call. Just go and do your thing and come back at 6 minutes past 11. Thanks, everyone. Okay, welcome back everybody from that short break. We're going to go straight back into the presentation, and we're going to be hearing from the team a little bit more around those kind of learnings from the project, the challenges, how they were overcome, and how you can best avoid them. If the presenters can please pop their cameras and mics back on.
Cameras on or just the speakers?
Just the speakers, yeah, sorry. Thank you.
Okay, let me take control. Okay, so we're just going to run through some lessons that we've learned up to now in the project. So the first two kind of go hand in hand together, but often technical discussions do require deeper exploration, and they may take multiple sessions to reach a well-informed decision. So it's kind of key that these aren't restricted to short 30-minute meetings, even though everyone likes a short meeting. And then also it's important to make sure that you're setting time aside to provide regular updates to everyone involved in the project, and keeping clear meeting minutes just to make sure that everyone's kind of keeping informed and everyone's on the same page. We've also found we expected there to be a kind of standard size and dimension of manhole, but we found that they do come in all different shapes and sizes. So it's kind of key to make sure that the kit is as flexible as possible to make sure it can be adopted across the networks. And for us, this involved redesigning the dock, as we mentioned earlier, to be more modular, so it could be assembled within the manhole chamber and wasn't restricted by the dimensions of the entrance. Our next point is that sometimes it's worth paying more upfront to avoid setbacks later down the line. We were using DIY sealing kits to keep the equipment watertight, but we found out pretty quickly that they were just no good, and actually we needed to invest in custom seals to avoid us having to repair the equipment later down the line. Slow isn't necessarily a bad thing. We're sending our data up to the control unit without changing the communication protocol that we've got in place already. And although this is a slower process, it does mean that the sense and development and integration could be started a lot earlier in the project than if we'd have then had to implement a completely new protocol across our system. ATEX certification also takes significant time and cost, and to speed up our prototype development, it's better to work in pre-approved sewer areas where non-ATEX equipment can be used, or use a water network where all the pipelines are non-ATEX to begin with. It's also important to explore supplier options earlier in the project to avoid delays in the supply chain. So the microphones that were chosen at the start were out of stock once we began development, so we then had to source alternatives. So it's important to do all of that as early as possible, really. But on a more positive note, working on this project and with University of Sheffield in particular has enabled us to support the development of new technologies without us needing an in-house testing facility. We've built a supportive, productive relationship with the uni, which we hope will continue to grow over time, and also give us the chance to explore more technologies that we may in the future then be able to integrate into our equipment. We've also had the chance to broaden our supplier portfolio and develop new relationships with local businesses that we can hopefully, again, use in future developments. And then I think it's over to Sonia.
So challenges we have to overcome as a group, and I fully agree with Jas. We work well as a group of companies delivering very interesting and high-risk project in a way, because that's the nature of something that's unknown. So what we thought is going to be an easy task: find the manholes, which are suitable to do testing and install host robot turns out to be quite complex task due to manholes we had to disqualify due to lateral connections, shallow depth, steep benching or obstructive access steps. This is probably something we are not going to have as a challenge in the next project, as robot is going to evolve into more advanced design. Some of these suitable manholes were positioned in the middle of the very busy road or on driveways, and since this kiosk is significant in size, we could not just install it anywhere. Also, there was a requirement, just one of many, to have 400-meter straight stretch of sewer, so we can test robots going downstream and upstream for 200 meters, which is requirement due to constraint introduced by FEDER length. In the same time, we had to preserve ATEX compliance, and originally we thought that FEDER could live in a manhole, but no, it couldn't. So it's now in a kiosk, introducing additional challenge because that FEDER now needs to be positioned in a kiosk, but then have a link to the manhole, which is sealed. We proposed U-shaped connection pipe, but then working with Binnicam, we realized that this is going to cause too much friction for FEDER, and we create a different design, which is straight pipe. All of this we had to test at iCare, which is Sheffield University test center, which is great luxury for this type of project. So we are sure that it's going to work in a field. Also, we had to work with Northumbrian Water standards team, as this kiosk, although it's innovation project, it has to comply with all standards which are required for any other kiosk with Northumbrian Water would install in their network. So next is Chris.
Yeah. Perfect. As Sonia said, I just probably best to touch on. I joined kind of partway through the project, and it has been a really great experience because we've got such engaged stakeholders in this project that are really motivated and passionate about the work that we're doing and the kind of capabilities that we've got. So that's been really great for me to join and be part of and welcomed in. And I've certainly enjoyed benefiting from the team's really in-depth subject knowledge, which I think has also been a key point. I think things for us internally at Northumbrian Water, we've been able to engage with lots of teams, people in the business, to speak in different forums, and really to make sure the business is aware of the project and what's going on. And then people have been able to ask questions with us to engage, to bring points and say, well, actually, what about this? And as Sonia just said about the site selection, something that we've been able to set up is a technical steering group. So that uses our sewer technicians and technical advisors, and we're able to update them on the project and be able to then gain their knowledge, their experience, and particularly around things like site selection. They're out in the field a lot of the time and know the practicalities of the locations and manholes. So we've been able to utilise that to really help us push on with site selection. On top of that, something else that's perhaps a lesson, but something that we feel we've done quite well as a project is the engagement, and that's possibly down to the imaginative nature of the project. And I know Clive said about the Thunderbirds and Wall-E reference. It certainly seems to have helped us when engaging with local and national media, and just being able to make sure that people are aware of the project. Because I said in my bit earlier on, the socialization and the idea of a robot in the sewer can be a bit daunting, certainly to people in the public. So it's something that we're wanting to ensure we've communicated well, and in that positive way, so that when it's outside a customer's house in the sewer pipe, they kind of know why it's there and understand that it's that positive thing that's helping us in that way. And also something that we were, I was going to say fortunate, but it's something that happened at our Northumbrian Water Innovation Festival, was Emma Hardy, the Water Minister, actually paid a visit and had a chance to engage with the team and also see a demonstration of the Pipebot robot. So she did that kind of during the summer at our festival. And then at the recent British Water Annual Conference, mentioned Pipebot as one of the standout projects in the quote just on the bottom of the screen there, saying that it was one of her favourites, and really highlighting it as something that she loved and is looking forward to seeing progress and be used further. So the fact that we're reaching all those different avenues to engage with people is really positive, especially moving forward. And then just the bottom point for a final lesson from us is the significance of anticipating the impact of the project. So many projects might be able to be incorporated into business as usual quite easily, but Pipebot Patrol is more transformative and may change the way that we work. So we're engaging with our planning teams around AMP9 and how we plan for wider use and expanded areas that Pipebots kind of work in. So they're able to include that as part of their planning and be able to foresee the future where we have many more Pipebots in use. So I think they're all the lessons learned that we wanted to sort of put. Clive, do you have any comments that you wanted to add from a Northumbrian Water side?
Yeah, I think the customer area was one of real interest. So when you get into a project like this, the views of the customer and the attitudes of the customer to having a robot in the sewer outside their house actually comes to the fore. We wondered whether there would be any resistance to it. Particularly, is the robot gonna listen in on me? Is it gonna pop up through the U-bend of my toilet? Can it see into the house? Those kinds of things. So we initially did a very early stage customer focus groups, and what we discovered there was quite the contrary. That customers were actually really, really interested and quite enthused by the whole idea, very, very interested in how it would work. There was no real concerns, and we did actually confront customers with, do you, in the end, because they didn't mention it, do you feel this will be spying on you? Have you any concerns? The answer was an emphatic no. And in fact, it was more, will you put a town hall style presentation on when you come to our area so that we can bring our kids down to have a look at it? There have also been suggestions that we name the robots to make them almost more sort of human friendly things. So attitude is incredibly important, and we've seen that borne out through some of the external communications we've done about the project in the early stages, as we've reached certain breakthrough points. There was a BBC article on their website, which in the weekend that it was released, which just basically described the concept and that we were working on this. It got 35,000 hits in the first weekend, and they approached us about doing more on it because there was such an appetite and interest. So that's very reassuring to know that. Again, in terms of overall learnings and lessons learnt, principles have been gained. We've learned a lot of things. We might have done a few things differently if we were to do it again. But we're essentially only 2/3 way through the project, and we're about to enter a really intensive learning period, which is in the sewers, the hard-earned, battle-earned learning of what does and doesn't work in the sewer where it worked in the laboratory or in the test rig. The one thing that's probably taken me most by surprise was the choice of trial zones. So I put in the original project plan quite a short period of time to select 3 suitable zones, and then a suitable amount of time to supply them with power. Actually, in the next phase of the project, we're starting, if we're funded, we would start 6 months before the project even begins to try and identify these zones, because it takes so long and the criteria became quite complicated, mainly because of the tether. So we won't see that so much in the next phase, but finding suitable launch zones, not at the foot of somebody's drive, not in the middle of the road, not with certain kinds of benching, not with too many connections, of the correct diameter and so forth. We decided that we wouldn't go for very, very complicated, trouble-ridden hotspots. Initially, we would go for one of each kind, a surface, a foul, and a combined sewer that were average, and see how they coped in those kinds of environments. So also we would allow much more time to supply power and data in future to any sites that had a kiosk, and there will be 1 or 2 in the next phase, in the very early stages, to allow us to test early. That's all I really had to say in terms of lessons learned. But I've seen there have been quite a number of questions asked as we've gone along, and we've hinted an answer at some of those. But probably I'll hand back over to Leah now to take us into the next part.
Great, thank you, Clive, and thank you to all the presenters as well. We've had a lot of questions, so jumping straight into the Q&A. Can I get all the presenters to turn their cameras on, please, for this part? And I'll stop sharing the presentation so you can see their lovely faces better. Perfect. So, first question from Dermot is this an untethered solution as of yet? I think you might have touched on it in the presentation, Clive, but just to confirm.
Yeah, I mean, untethered at the moment, it's not really a solution yet. It will be in the next phase, but in its current form, it is very clearly tethered, and that was by design. And more than anything else, we want to cut and dispense with that tether. Now we've learned what we needed to learn through it, or are learning.
Perfect, thank you. And Shane, what length of sewer is it planned to travel prior to returning to a base location?
Yeah. So right now, this one is it can do 350 meters. We can upscale that to 500 if we have the room to put the cable reel, and then I think moving forward with the tetherless solution, that's very dependent on how big of a robot we want to make, on the power we can hold, but we hope to go further. So that's a lot of manhole chambers. So yeah, 350 for now is the answer.
It's worth noting that, if you look to e-scooters and the size of the battery and those kinds of devices and the weight, the payload that those scooters are taking and the distance they can go, it doesn't take much imagination to realise that we should be able to go considerably further than we currently are. And it's also worth noting from the question, it sounds like, prior to return to base, the robot is designed to be patrolling all of the time. So we wouldn't imagine it sort of going out on a patrol, coming back and parking in its chamber for 4 hours. It will be off and out and patrolling a lot of the time when it wasn't charging. It doesn't need to come back to its base station to download data or anything. It can do that where it is. So its mode of operation also is that as it patrols round, potentially on day one, a completely clear zone, when it identifies something of interest, it will create a point of interest on the dashboard, which it will then monitor and pay a little bit more attention to the point of interest to see if it's getting bigger, smaller, moving, what it's made of and so forth, and build that information up over a period of time through its repeated patrols.
Great, thank you, Clive. Great insight to add. And another one for Jess or Shane, I believe, maybe Kirill too. What diameter can it go down to and up to in terms of pipe size?
So the prototype that we have at the minute for the field trials, that's designed for 300mm pipes, but it can go up to 400mm as well. We do have what's called a cradle, so you essentially sit the crawler on top of a cradle with big, huge wheels, and that will allow us to go into the bigger pipes, but that's not what it's been designed for at the moment. And then we do also have the linear array of the microphones and acoustic sensors, so that although we can't go into the smaller pipes, we can still analyze what's up there using those sensors on the side of the crawler. So although we can't go into the smaller ones, we can still get an analysis of those pipes as well.
As part of this project, we're building what Clive calls acoustic ray gun, so to send acoustical signals into the lateral connections to find the integrity and lengths.
Perfect, thank you. And next question from Carol, I think this one's for you, Shane. What thought has been given for the effects of trade effluent and potential high or low pH streams in the network?
Yeah, so difficult one to answer. Our crawlers are already used extensively in the network, so they're designed with corrosive resistant materials with the greases that will resist them. So quite a lot of thought by the fact that we've based it off what we know very well already. But it's fair to say in highly corrosive environments, it's difficult. It is massively difficult. So they will be problematic if it's particularly corrosive. But general use and general norm, trade effluent and all fine. Yeah.
Great, thank you. And while I have you, Matt has also asked, what would the thoughts be on using the system in sludge lines, typically dry solids from 1 to 9%?
It's similar answer where our crawls are already used in sludge conditions. Jess touched on it a little bit. If it's particularly bad, we can use a cradle, which has got a lot of ground clearance, quite narrow wheels that are spread quite wide apart, so they kind of run along the edge and away from where the sludge is, so it can move along. But yeah, absolutely not a problem. But I would say in sludgy conditions in the smaller diameters are a problem because you struggle with ground clearance, you struggle with the size of your wheels. So if you came up with just a small section, that's where the acoustics can actually detect quite a long way. So we can kind of not necessarily go through the sludge, but look beyond it as well. So a few mitigating things.
Perfect, thank you. And in what way does the Pipebot resolve challenges associated with a backdrop manhole? Is that one for you, Clive?
Possibly, yeah. I mean, Kirill may also have something to say about it. The recognition of backdrops was really crucial in the early stages. We realized there could be all sorts of obstacles. If the robot was lost down a backdrop, for instance, obviously it's going to be a problem. So Kirill has equipped it with a LiDAR scanner, which is looking ahead constantly, basically for unmapped or unknown drops, dips, places, cliff edges, in a kind of cliff edge detection mode. Kirill, do you want to add anything to that?
Yes, well, you're right, Clive. So, the addition of acoustic sensors, we enable to detect anomalies in the pipe, so many meters ahead of the robot. So it can actually begin to anticipate that something is happening. LiDAR itself is able to detect this kind of anomalies and classify them. So approximately not half meter, 0.8 meters away from the robot. So therefore, for the robot, there is a opportunity to stop and examine whether it can overcome that drop or not. The next generation of robots we're planning to build may be able to overcome some of the drops. And if the drop is too high, so in this case, the survey has to be abandoned and taken from the other side of the drop.
Great, thank you, Kirill. And another one for you from Gosia, who wanted to ask, what proportion of blockages can the robot potentially detect? That is the proportion that occur in pipes for which the robot is suitable.
Well, the two don't equate, because the robot is designed to detect blockages in any pipe, whether it's in that pipe or whether it can just see up that pipe with its acoustic ray gun, as I call it. So theoretically, it should be able to detect all blockages. It may not be able to deal with them, but it can do two things. If it detects in a lateral, for instance, build-up or debris that is concerning, it can alert us to that fact, and then we can decide whether to send a crew out and take a look at it with a human. We are thinking about, we've included in the next phase of the project a small piece of feasibility work on the launch of a child robot. So we will actually be looking at that. And the theory there is you drive the robot to the lateral, you detect the laterals with the acoustic tool, and if you detect a blockage, you dispatch a child robot up that very small pipe where the host robot can't get because it's too big, but the small robot can, and it takes a much closer look.
Great,
Don't know
thank you.
if the team have got anything else to add to that one.
Yeah, the use of marsupial robot is a definitely a possibility, which we explored a while ago when we had a project called Pipebots from Engineering and Physical Science Research Council, upon which these Pipebots are built upon.
Perfect, thank you. Great, and next question from Farhan, who wants to know how much is the cost per robot potentially? Have Northumbrian Water assessed if the cost of having the robot outweighs the implications of sewer flooding, fixing assets reactively rather than actively once they fail?
Are we saying, Shane, do you want to take that? Are we saying how publicly how much the sort of prototype level robot costs?
No, we'd want to. I think it's not that. I don't think the prototype costs are not that useful because they're really high because of the low volume. I think we'd expect them in line with the additional sensing and cost of that isn't great. So we'd expect sort of 20-30% higher than our normal inspection systems. But I think it's more of a question of, are we doing this for the sake of cost, or are we doing it for the sake of what the environment we're acting on and the impact to our customers? Because the cost of sending things out and the cost of a crew is one thing, but the impact to a customer having one of those first photos of having a load of poo in your bathroom is not particularly nice. So I think they won't be ridiculously expensive. They'll be cost competitive to normal inspection systems, but it's more of the application that I think we start to gain real value from.
It's worth pointing out that the development costs, much of the development costs so far, have been borne by the Ofwat Innovation Fund, paid for by English and Welsh water company customers. We could never have done this project if it wasn't for that fund. The risks would have been way too great. This is a particularly risky project. And if you're sort of looking at a cold, hard business case, it wouldn't pass muster within a water company because we would be too conservative about it. So the fund has allowed us to tackle, like, what we're trying to do here is really ambitious. It is eradicate blockages in AMP9. Okay, that that's quite a business case if you look at the costs. This is eradicate sewer flooding due to blockages, okay, as opposed to hydraulic capacity or other causes. Actually, from where I'm sitting, is looking quite doable if we get funding for the next phase of the project, and we've included in the latter stages in our work package, which is around adoption and wide scale up, quite a lot of effort around working on the business case and ensuring that the cost of adoption is kept low, as well as the actual unit cost per robot, as well as commercial considerations. So we haven't yet decided if it's best for a water company to buy robots and deploy them themselves, or whether it is to buy a robot inspection, autonomous robot inspection, sewer zone maintenance as a service, because both would be possible if people were in the market to do that. So those are obviously going to affect the business case and the way of doing this.
That's great, thank you, Clive. And coming back to you, Shane, are there flotation issues within the unit? We have sewers surcharged all winter and most of summer due to infiltration and ingress, and fog settles on the top third of sewer. Have these sort of issues been considered?
Yeah, no, there's not significant flotation issues. It sinks like a stone. It's very heavy. I think it's hard to give a scale, but the crawl's 140 millimeters. Fits in a 140 millimeter pipe in its standard form, and it weighs nearly 20 kilos. So certainly doesn't flow. But I think a lot of that is high flow. How well do the acoustics work in really high flow environments? That I think that's a challenge. The fog, some impact on LiDAR, we think, but we also have the backup of the optical. So it's a sensor combination that kind of helps us mitigate some of these situations. Although that scenario that you've described there, very challenging for anyone to do anything about. I would say that is a very challenging situation.
Great, thank you. And a question from Karen. Oh no, sorry, we've gone through that one. A question from Colin. Although the unit has stabilizers, do you expect it to navigate bends in manholes without tipping over?
It's two questions there, isn't there? There's, do you expect it to navigate bends and without tipping over? So yeah, of course, it has to be able to branch. If it's going to patrol the whole network and the network branches, it has to be able to make those decisions. It has to go back and forth between the various branches. And in the latest design, we're looking at an articulated design with universal joints between the carriages. So we segregate the battery holding carriage, if you like, and nose cones either end, so it can go in two directions. But that idea was born of the battery size. If you start introducing more and more batteries in order to power the thing, that it gets longer and longer and less able to negotiate bends and corners in the network. So you then have to look at ways of articulating it and obviously minimizing the size of the battery, minimizing power consumption, so you don't need to put so big batteries in it. But yeah, and in fact, yes, it could, and we will find out in the extensive sewer trials and extensive sewer trials in the next phase of the project that it can negotiate bends without tipping over. And I have absolutely no doubt it will tip over, probably within the first 2 or 3 days of going into the first sewer. That is the point. So our approach to developing survival for 30 days is expect everything to go wrong, iterate, take the thing out, understand why it tipped over, how it tipped over, and implement a sort of corrective improvement to the design. Of course, before we ever get anywhere near the sewer, it's been extensively tested in the lab, and it's also been extensively tested, or will have been tested, in the test rig as well.
One of our mitigation measures is to use inertial measurement unit, which gives information about the tilt, and it informs the control of the wheels and the motors which control the wheel. And that's something we looked already together with Minicam. So there is actually a possibility to take into account locomotion over a bend. Yeah,
that's absolutely right. The things don't just tip over on their own. It's driving itself, so it knows if it's going to tip itself over, and so it can take some mitigating action there.
Great, thank you. And how do you expect to cover more of the network as you do scale this up, or will there always kind of be limitations to how much can be covered with this solution?
Yeah, so it's bounded by a number of things. Us in sewerage operations team, where we could literally draw a polygon on our GIS systems and define the zone that we're allowing the Pipebot to roam within, that particular Pipebot. And you can imagine that there could be multiple adjacent zones within the sewer network with multiple robots operating in them. So that would be why you don't need it to go on forever and ever, because we don't imagine one robot patrolling the entire network. We're going to need lots, hundreds possibly in future. Not every zone would be patrolled by a robot. If there's no bother, and it's fully operable all the time, there's no point in putting a robot in it. These are aimed at places, they're aimed at prevention of flooding due to blockages. So it's where you get blockages, that's where we would deploy these robots and target them. It's also worth knowing that the design has been redeployable. So if you go into a zone that has problems for 30 days, or maybe to put 2-3 cycles, 60-90 days worth of patrol, you might decide at that point, you know everything there is to know about that zone. And therefore you want to take the entire solution, manhole cover as well, into a completely different zone. You now understand that you've resolved the problems in that zone, and hopefully for the time being, maybe we stick the robot in for another 90 days to prove that there are no problems anymore, because the root causes have been dealt with. But when you get to that point, you can go to another zone with the same robot. So it's a redeployable, reusable solution that can be moved around by presumably in the future the robotic maintenance team or a robotic sewer monitoring team in AMP9, I should say. I'm not talking about tomorrow.
Absolutely, yeah, that's great. Thank you, Clive. A question from Peter: how will it manage high sewer velocities to avoid being swept away? Is that something we've already touched on? Sorry.
No, it's not. So I think, well, currently that's quite easy because it's on a cable. So it doesn't really get swept away because it can anchor itself. I think the concern more is probably on the next phase where we're trying to go tetherless. I think there's a proactive method is what we've been considering. So we talked about weather forecasts, tying that into whether it should be patrolling right now or whether it should be in its dock hiding away pretty much. Modelling around those weather forecasts as well, so that understanding it's not just instantaneous, is it? With a downpour, it lasts quite a long time. And then there's the physical design of the system. So again, we design these to be heavy and robust so that they don't just get pushed away. But there is also there's a limit to that. There's a lot of power in water. So yeah, I think the only practical solution is to hide away in high flow situations, to be honest.
It's a great question, that, Peter, because it begs the question: what is the flow required to wash the robot away? Okay, so that triggers some thinking around testing of the robot in the laboratory environment and just increasing the flow until eventually the robot does get washed away. So you have to understand that sort of force is required to wash the robot away of a given size and with a given coefficient friction between its wheels and the sewer pipe itself in various conditions as well, because if it's slippery, it will get more easily washed away. We can do that. We can test that in the lab. So we will know that part of the equation, and that would inform the sort of weather forecast prediction of the flow in the pipe and the recall command being triggered that, well, we think there's a potentially wash away incident about to happen. Let's recall the robot before that storm arrives on a matter of precaution. Whether or not it actually transpires is another matter. So thanks for the question.
Great, thanks, Clive. Kirill, coming back to you, Rachel wanted to ask acoustic detection and blockage recognition in the air path, underwater, or potentially both. Could it report back to water level in the future?
Acoustics can definitely report water level, and it also combined with the LiDAR measurements, which will reflect from the water level, will provide very accurate assessment of the water level in the pipe. Detecting something underwater is more challenging, and remember I mentioned that using inertial measurement unit, so the robot drives over the sediment, can help to understand what exactly driving on and how high it is. So using LiDAR and acoustical data combined together, fused together, will provide extra information. Yeah.
Great, thank you.
I hope it answered the question.
Clive, coming all the way back to the beginning of the presentation, hopefully you'll remember you had a slide that had a lot of speech bubbles on it from feedback you've gathered.
Yeah.
There was one that was mentioned about potentially this being a blockage. Did you answer that in your think tank at all, and how was it answered?
Yeah. So the bubble was the robot will become the blockage. I think that's the one we're talking about here, isn't it?
Yeah.
So in Pipebot Patrol 1, it hasn't really been much of an issue because we've introduced sort of the highest priority message that the robot gives is I'm stuck. Okay, and that's like immediately actionable. Plus, it's easting and northing, its position within the sewer, so we know precisely where it is and we could get there. And that would be treated like a blockage. It is possible that it could be the blockage. The other thing is avoiding situations where it's likely to become blocked, and that is the learning that we're about to go into with deployment of the robots to the sewer, which is where we get some practical first-hand understanding of the likelihood of that of the robot becoming the blockage. It's probably more of a challenge and a greater risk in Pipebot Patrol 2, where you haven't got the tether to pull it out, or not initially. Again, what we're thinking about is being classically cautious and risk averse, that when we deploy the tetherless robot, it has a tether, but not a power and data tether, just a cord, until we're really sure that it's able to not get itself wedged. I mean, if you talk to one of the partners on the project, who we haven't named on the header sheet, is Fastflow, who operate CCTV crawlers all day, every day, human propelled, admittedly, and so we relying on their knowledge, this all day, every day deployment of hand propelled robotics in the sewer, to advise us how frequently that occurs. And it doesn't occur very often, as often as you might think, and it isn't impossible to get these things out. We did include some thinking about taking control of the robot. So remember, it's not driven by a human, it's autonomous. It's there on its own, it's driving itself around. But it would be possible with the controls and the communication that we have in place for it to send a distress call to say, I'm a bit wedged here and I'm not, I can't get myself out. And for a human to then take remote control of the robot and drive it out and look through its camera to see what's going on in real time and pull it out. Now, we haven't perfected that. We haven't done much experimentation, but it does remain as a sort of idea on the shelf for how we might get it out of that situation if it occurs. But worst case scenario, gets wedged in there, we'll treat it just like a blockage. Except in Pipebot Patrol 1, it has got a tether, so generally we're going to just be able to pull it out.
Perfect, thank you. A couple of questions have already been answered in the chat, but I'm just going to circle back to them while we've got 5 minutes, just in case anybody missed them in the chat. So Kira, coming back to you, is it possible to add acoustic sensors to measure the thickness and condition of the pipework as well?
The condition is possible. As a matter of fact, the roughness of the pipe can be measured from the acoustical data right away. So unfortunately, if the pipe is filled with mainly air, so there is very poor coupling between sound waves in air and sound waves in the pipe material. If the pipe is filled with water, So then the underwater acoustic sensor ultrasonics can be used for that. Alternatively, there are some studies which we're doing at the moment suggest that the use of radio frequency sensors like a ground penetrating radar might be a possibility. But using acoustic sensors, airborne sensors, it's a challenge.
Great, thank you. And Clive, can this be Regulation 31 approved to use in clean water potentially, or is it purely for use in wastewater network? I know for now it is, but in the future.
So it most definitely is. It is a sewer system solution. We've never had any aspirations to exploit this on the water network. Although again, it doesn't take a genius to realise that if you can affect autonomous operation, you might want to try and transfer that to the Reg 31 environment of the water network, but absolutely outside of the scope of anything that we're doing. And we're not really thinking about that too hard. We're thinking we're 100% focused on sewers.
Absolutely, makes sense. Great. Well, I think that's all the audience questions we've had today. So thank you so much to the audience for asking those really great questions. We hope you've found this session useful, and we hope you found the presentation insightful and valuable too. I just want to say a quick thank you before we leave today to the audience again for taking the time out of your day to join us today, and to ask again if you can please make sure to fill in the feedback poll before you leave, so we can make sure that we're doing the right thing with these showcases. That link will be put in the chat again for you. Thank you again also to our presenters for the time you've taken to put together today's presentation, and for sharing so openly and honestly about the learnings behind this project. It's been a really great presentation, so thank you. And yes, for everybody asking, we will be popping the slides on the Spring platform alongside with the recording from today. There's usually about a week turnaround for Spring to edit the recording and to get the case study together, but that will be available for everybody to view within a week or two from today. Anybody who's interested in asking more questions, please feel free to direct them towards me, email me any questions you've got, or if you'd like to be introduced to any of our speakers today, and I can kind of pass that back to the team for you. Other than that, I think that's the end of us. So thank you everybody again, and have a lovely rest of your day. Bye.
Thank you very much. Bye.
Thank you.
Thank you for the questions.